So for this problem statement, we have determine the maximum load P that can be applied to the sling having a negligible thickness so that the normal stress in the post does not exceed the allowable stress of 30 megapascals. The post has a diameter of 50 millimeters. So we're being asked to determine what is the maximum P that could be applied to this rope or string, whatever you want to refer to it as, such that it won't exceed the maximum or the allowable axial stress of 30 megapascals. So this is another case where you're going to have a axial stress associated with that, but also additionally, since this is offset from the center of this rod, it's also going to be causing a moment. So you're going to have the axial stress plus your bending stress, and this is equivalent to the total stress going to be developed in this rod. And this total, of course, since we were given this is going to be the maximum allowable axial stress that could be developed in this object here. So we already have the allowable axial stress. And the axial stress here is pretty straightforward to calculate, right? We have the P divided by the cross-sectional area, so let's go ahead and do that. So of course, since we're trying to solve for the maximum P, the maximum load that could be applied, we're going to leave P in variable form. So this is going to be the actual stress plus we have the bending stress, which is the moment times c divided by the moment of inertia. And this is equal to the allowable stress here. So first off, for the moment itself, the moment is going to be equivalent to that force P. Now the question is, what's going to be the distance from the center? Well, since it's going to be applied at this point here, right at this point below it in terms of the cross section, we know the moment is going to be this direction here with respect to this axis here, right? So this is going to be the neutral axis where you see point A. So we know the stresses are going to be zero. The bending stress is going to be zero at this point. And we know that point B is going to be in compression and this other point opposite is going to be in tension. Now you could always draw it out just to make sure you're understanding the problem correctly. So let me go ahead and draw out this beam, however, in a different orientation. So now here I went ahead and drew the beam. We have this load P, which causes a moment this way. And essentially that means is going to be in bending this way, just exaggerating the deformation, right? So we know that the top portion is going to be in compression while the bottom is in tension here. So now the question here is, when we're adding up the stresses developed, the axial stress and the bending stress, are we going to be adding up the compressive bending stress or the tensile bending stress? In this instance, since P is an axial stress and it's going to be tensile, it's going to be lengthening this rod, then in this case, we'll be able to calculate the maximum stress developed utilizing the tension. So in this instance, we're going to calculate the bending stress and consider only the tension, not the compression, because if you were to add up the compression would be a negative value and your P will be a positive value. In a sense, they're going to cancel a portion of it out, and therefore you're not really going to be considering actual maximum stress developed. So going back to the moment is equal to the force P times D. In this case, since we know the neutral axis is right at the center, in this case D is going to be the radius, right, from the center to that force here, the perpendicular length to P, which gives us P times 0.025 meters. And of course, we're going to keep this in variable form. Now, the C value here, in this case, we're looking at the tension portion of it. It's going to be from the neutral axis to this is going to be your C value, which we know it's going to be also the radius here. And we also know the moment of inertia of circular geometry. So let's go ahead and plug all of this in. So now that we plugged in all these values, left p in variable form, let's go ahead and simplify this and factor out the p to make it simpler to solve for the unknown, in this case p. So the maximum allowable axial stress is equal to p times 2546.48, which is the value we get once we multiply and add them up. And just keep in mind the units. In this case, we have meters squared at the bottom, so it's 1 divided by meters squared. This is important when it comes to canceling out the units because we know the maximum allowable stress is 30 megapascals, right? Or you could write it in terms of kilopascals or kilonewtons per meter squared. And to solve for p, we just divide by this value here. The meter squared actually cancels out, and we end up getting the maximum p value being equal to 11.78 kilonewtons. So this is the maximum force that could be applied such that we don't exceed the allowable stress of 30 megapascals. So I want to revisit the reasoning behind adding the tensile portion of the bending stress instead of the compressive portion of it. So let's go ahead and draw this rod again, but in this case we're going to be drawing the stress distribution along the rod in both the axial and the bending stress situations. So we see for the axial portion of the stress, it's going to be tensile stress. So we're pulling this rod or stretching it. So this is going to be going upwards, right? Let's say this upwards is the positive stress direction. Now, when it comes to bending, we know that a portion of the rod is going to be experiencing tensile stress. Let's name it tensile stress, and the other portion is going to be experiencing compressive stress. So going back to the direction, right, upwards is positive. What is going to give you the maximum stress that develops in the rod? Well, in this case, you're going to have the axial stress because it's going upward, and the tensile stress due to bending. Because if you add up the compression, it's actually going to give you a smaller value because it ends up canceling out some of the axial stress developed. And so this is the reasoning why we go with the tensile stress due to bending to add up with the axial stress to determine the maximum stress the rod will be experiencing. Now, in certain instances, it does depend on the case, right? If we're having a compressive stress, axial stress in this instance, then we would also want to add it with the compressive stress due to bending. So it is, in fact, on a case-by-case basis, depending on what you're trying to solve for and all the other parameters. With time, this will get a little bit easier to identify.